Hi again, everybody. Chris Tisdell here again. Thanks for tuning in. In this presentation, I'm going to share with you some forthcoming mathematical research of mine. And in particular, I'm going to address the question, when do fractional differential equations have solutions that extend? Another way, how can we extend solutions of fractional differential equations? Now, you may not have ever heard of a fractional differential equation or the idea of extending a solution. Don't worry, we'll talk about that as we go along. Now, this presentation is based on a forthcoming paper to appear in the Journal of Classical Analysis, and I'll put a link in the description when the paper has been published. So let me share my screen with you and we can get down to business. By the way, just before I do that, the audience for this presentation is sort of undergraduates or advanced undergraduates and research students. I'll try to keep it at a level that's reasonably accessible. Okay, so let me share my screen with you. Okay, when do fractional differential equations have solutions that extend? So I won't be giving a full answer to this, but I'll be giving up a partial answer. All right, so first of all, we know what a differential equation is. The idea of a fractional differential equation is just the idea of a derivative that doesn't have to be a whole number. So for example, you could have a derivative that is order 1/2 or order 3/4 or order 5/3. Okay, these are the ideas known as fractional derivatives. And when you have a fractional derivative, then you can couple it with the right-hand side and you can form a fractional differential equation. Okay, now we are going to look at conditions under which the solutions to these fractional problems have a maximal interval of existence. And again, I'll talk about that a little bit more as we go through. Okay. Now, the conditions that I'm going to introduce and the innovation is a new growth condition on the so-called right-hand side of the problem that ensures the solutions will extend. And the ideas involve ideas from classical analysis, and in particular, and you might be surprised about this, the divergence of an infinite series. Now, yes, the divergence of an infinite series, not the convergence, the divergence. And this reminds me of a famous mathematician called Oliver Heaviside, who was one of my favorite mathematicians, who had a special quote, this series is divergent and therefore we may be able to do something with it. Let me just show you a quick picture of Heaviside. So Oliver Heaviside liked the idea of divergent series, and so do I, because the basic idea in this research presentation involves the divergence of a series. So divergent series can be useful. Okay, let me share my screen again. Okay. All right, so this is the problem we are going to look at. It's a bit of a monster problem. The order is Q, which is the just positive, so it could be a fraction, it could be a whole number. This dq is the so-called Riemann-Liouville fractional differentiation operator of arbitrary order Q. This T operator here, or T sub ceiling Q minus 1, is the Maclaurin polynomial of X of this order here, where we have the ceiling function Q minus 1. And you'll see here in the bottom row, you've got regular order derivatives, okay? So you've got a fractional differential equation in one, but you've got regular integer order derivatives in part 2. Now this, you might think that's a weird combination, but this combination was suggested by a mathematician called Caputo, who realized that the initial conditions actually model phenomena better when they are actually originally, when they are the integer orders are there in the derivatives, okay? And the AIs are just constants. So this is the problem. F could be F's going to be assumed to be continuous and perhaps non-linear. Okay. All right. Now, firstly, let's look at this definition a little bit more. In fractional calculus, you have the concept of a fractional derivative, d sub q, which is given here. Now, you'll see that you've got an integral, you've got these regular derivatives here of order ceiling q, and you've got the gamma function here. Now, when q is an integer, these things just all cancel each other out, and you just get the regular derivative. Okay. Now, like you would expect in any kind of calculus, if you have a derivative, you should have an integral. This iq is the fractional integral of order q of this function y. Okay. And sometimes this left-hand side here is reduced to this Caputo derivative, where you just basically this gets compacted down to here. Okay. Now, again, if q's an integer here, the derivative of this Maclaurin polynomial just disappears. Okay, so you get the regular derivative and regular differential equation that you would be used to. Okay, so I'm just going to step you through a few preliminaries here, just to set up the notation and make the ideas a little bit more clearer. All right. So we are going to look at a particular rectangle, which we're going to denote by R. So R is going to be something like this, where it's sitting in two-dimensional space. You've got, say, an A naught there, and you've got a little a there, and you just draw a rectangle out there, and this sort of width here is B. And so R is essentially going to be some domain of this F, which we might restrict F to. And we're going to make the assumption that F is going to be a continuous function. Because this is a compact set, we know that F is bounded on that set. So M, this M is going to be the number, which we know exists, such that F is bounded on that rectangle by this M. Okay, we're going to rely on the following theorem a lot. It's a famous theorem, first proved by, who proved it? Let me just see. It was Tisdell and Ford, and it's basically known as a local existence theorem. Okay, let me share that with you because it's going to be a big part of our presentation. All right, we're going to need the following so-called existence result. Now, this result can be proved using Schauder's fixed point theorem as done by Tisdell and Ford, or as I've done by using Weierstrass's polynomial approximation. I'll show you these references at the end. Okay, so what is this theorem? All right, suppose F maps this rectangle into the set of real numbers and it's continuous. Then the original initial value problem here has at least one solution on this, that's x equals x of t on this interval, such that the solution stays within this rectangle for all t in this interval, where alpha is defined by the minimum of these two things. Again, you've got, the q here is the order of the derivative. You've got the gamma function again. M comes from here, and B comes from up here. Okay, now that's a big theorem. That's a big theorem to contemplate. It's just what's known as a local existence theorem. The main assumption that we make in that theorem is a small assumption. The right-hand side of the differential equation is continuous. Okay, so basically, really, the only assumption here is that F maps this set into the real numbers, and the right-hand side is continuous, which is not a huge assumption. Okay, and the conclusion is that there's the original initial value problem has at least one solution on this interval. Okay, So this is a local existence theorem. There could be one solution, there could be more than one solution, okay? We're only making one essential assumption there, so we can't expect the conclusions to be too grand. But we're going to use this theorem over and over again in our main result. So this is not new. I'll come back to that, but this is going to be very, very, very important. All right, so before we before we get to the main result, what do we actually mean by a solution? Okay, what if I've got a problem like that? What do I mean by a solution? Well, essentially, it's just a function that whose left-hand side of this equation is satisfied, the right-hand side satisfied. The two things are equal, and they also satisfy the initial conditions. Now, I've put it in a sort of a long-winded definition here. Okay. A solution to the initial value problem 1, 2 on some interval I is defined to be a function such that it's the qth order derivative exists and the points lie here and it satisfies equation 1 and equation 2. Now, our interest will be when I is either this compact interval or this half line, okay, up there. Okay, so we're making a little bit of progress here. Shall we? Let's move on to the main results. All right, so I'm going to discuss the main results now. Oh, let me share my screen again, sorry. Okay, so we're going to talk about the main results now. So under certain growth conditions on the F, we're going to show that the solutions to the original fractional differential equations have solutions that are defined on this whole interval or this whole interval. So this compact interval, this half line. Okay, so this is one of the main results. It's not like I'm going to present two results, but the following result I think is nice, and I've tried to keep it simple because the ideas for this, the proof for this result readily extend to the proof for the sort of half line result. Okay, all right, so it's a long theorem. Let's just go through it bit by bit. Okay, so let F be defined on this set and real valued and be continuous on this set. If there is a continuous non-decreasing function phi, which maps this into this, such that this growth condition is satisfied. So this is like a growth condition of F in the second variable, if you like, on this set. And this integral condition is satisfied. Then the original nonlinear fractional differential equation, the initial value problem here, has at least one solution that is defined on the whole of this interval. Now, note this interval and this interval. This is the maximal, it could be thought of as the maximal t interval that F is defined on. Okay, so the t interval there and there. All right, so let's just break that. This is like a growth condition, and this is like an integral condition. Okay. All right. So what we're assuming much more than the theorem 1, right? Here we really only assumed that F was continuous. Here we're assuming continuity. We're assuming F satisfies some growth condition and and the phi satisfies some integral condition. Note also that this growth condition depends on the order of the differential equation, which is kind of cool. And the conclusion is the fractional differential equation 1, 2 has at least one solution that extends to the whole interval where F is defined on in the t interval. Okay, now the proof for this is not short. It's a repetitive type process, but I can pretty much summarize the proof in one picture though. Okay, so let me show you. I might just draw a little picture, and the ideas rely on theorem 1. Okay, so basically, if I was to draw a little picture here, right, what we're going to do is start here, and let's say we're at a naught. I'm going to draw a little rectangle around there. And I know from Theorem 1 that there's a solution that stays in this rectangle, okay? Then I'm going to take another point here, and I'm going to form a new initial value problem. And I can draw a little rectangle around there. Okay, so think of this as sort of a T0, T0 equals 0. Think of this as T0 plus T1. I can start a new problem, and I can get a solution that starts and stays within this rectangle. Then I can keep going. You know, I'll get another rectangle there. Okay, another initial value problem, and it might go like that. And essentially what happens is you get these intervals, and these intervals will basically move out towards A. So the whole thing will get will extend over to the interval 0 to little a. That is basically the whole proof. Okay. So the proof that I'm going to show you is a little bit repetitive. We just keep hammering away, applying Theorem 1 to get all the local little intervals where the solution is defined on. And you put them all together, and basically that extends to the whole interval 0 to little a. Okay, so let me just go through that with you. Now, after this result, I'll show you the half-line result too. All right, so consider this general fractional initial value problem. Here, we are looking not at 0 in this particular problem. We've just got an arbitrary sort of T0 here. And this cow T is the Taylor polynomial of this order of x at t equals T0. Okay, and you just appropriately modify the dq in 3, okay, as I've said down here. Okay, so you form a general rectangle similar to what I had before, and this cal m now is the bound of f on that rectangle. Okay, and we know because f's continuous, this bound exists. Okay. All right. Now, since f is continuous on R by Theorem 1, we know that the problem 4, 5 has at least one solution on this interval where alpha is defined to be this. Okay, that's just applying Theorem 1. Okay, now we can start doing the systematic application on each little sequence. All right, let's try that. Okay, so this is like step 1, if you like. Let's reconsider this general problem by associating T0 with 0, X0 with A0, each xi with ai, and let's choose b equals 1. So now essentially I'm back to the original problem that I started with, 1, 2. Okay. All right. So, and I've chosen a particular value for little b in my rectangle. So I've got a rectangle here, which I've called r sub naught. We can form a bound m sub naught on f over r sub naught, be obtained by the growth condition. That was one of the assumptions in our main theorem, this thing here. Okay, so this bound on u just comes from rearranging this triangle inequality. And then this is the growth condition, which goes from here to here because phi is non-decreasing. That was another assumption. So that goes there, and I can have another inequality sign, and I'll define that to be my m0. Okay, I'm going to define this to be my m0. All right, now what? Well, the fractional initial value problem 4, 5 has at least one solution on this interval with T0 to be this, the minimum of this. Okay, again, this is just Theorem 1 here. Okay. Now, if we just sort of, the 1 on Q and the Q will cancel each other off, and you get this. Okay, so This then is the first, let me see if I've got it here. This is the first rectangle that I sort of drew before. So I've basically got, I've run the iteration once, and I've got the solution on a little rectangle. Okay, so now we keep going. All right, let's reconsider 4, 5 associating with T0 with T1, or T0 with T0 plus T1. X0 with this, we get the same, we choose the same value of B, and thus we form this rectangle R sub 1. And you can rearrange this to get this, and this comes from the previous page, and then you form a bound in the same way. Call it M sub 1. Okay, call it M sub 1. Right, so I've been up to here, and now I'm going into this rectangle. So I've got a new initial value problem. Well, we know from Theorem 1, there's at least one solution on this interval where T2 is defined by this. Okay? So now what we've got is a second rectangle. So we've gone there, and we've got a solution going into this second rectangle. What about a third rectangle? Well, I'll do it one more time. I think I'll do it one more time, and then we can do it. Okay, well, I'm not going to do it one more time. I'll do the general case now. Okay, so let's look at the general case. So the sort of the mth rectangle, if you like, or the m minus 1th rectangle. Okay, so if we keep on going in that fashion, we associate T0 with this sum here, X0 with this here, each xi with this, and we continue to choose B equals 1. Okay, we form this rectangle like that, rearrange that to get the bound on U, and you can form the bound using the growth condition again. Okay, so what does that mean? Well, it means in the general case, just by applying Theorem 1, the IVP has at least one solution on this interval here with T sub m, the minimum of this. Okay. All right, so we're making progress here. It's a little bit slow and a little bit repetitive, but we're making progress. But now here comes the good part where we can get onto the divergence of an infinite series. All right, so what we've done here is we have shown, if we continue this sort of little extension process in the rectangles, we've shown the existence of a solution to the original problem, 1, 2, on this kind of interval where T sub m is the minimum of A and this sum here, and T0 is of course 0. Okay, so what happens if we keep doing this in the limit? Okay, well, basically I'm summing up T1, T2, T3, T4, etc., etc., etc. I'll get this sum here, and this sum is infinity. Why? Because we assumed that the integral diverged. That is nothing more than something you would see in a Calculus 2 course, okay, in basic introduction to series. It's the integral test, okay? If this is diverges, then this sum must also diverge. Okay, so we've just applied the integral test for series. So what does that mean? It means that basically this goes off to infinity. And so if I look at the minimum of A and infinity, of course, the minimum of A in this sum is going to be just A. So what do we conclude? We conclude that the solution extends all the way over to the interval. So we can keep doing this out here, and of course we're going to get to little a eventually. Our solution is going to extend. All right. Phew. Okay. That was a long proof. Now, what can we do with the ideas on the half line? Okay, so the conclusion of this result, remember, was just the interval 0 to little a, the solution exists. Now, I won't rerun the whole proof for the half line, but let's discuss that because I actually find that a little bit more interesting. Okay, so if f is autonomous, so you can see here, f just depends on x, not t. All right, so that means that when we talk about independent of t, we say autonomous. Now, in this case, we can extend solutions over the half line by using a similar approach as in the proof of Theorem 3. So let me just talk you through that. I'm not going to do a full proof, okay? All right, here is the main theorem. This is the one that I really like, actually. Theorem 4. So let f, the autonomous f, map the real numbers into the real numbers and let it be continuous. Again, if there's some growth condition here on f, note f doesn't depend on t, there's some growth condition on f, and the integral condition is satisfied, then the autonomous fractional initial value problem has at least one solution that extends to the whole half line. Okay, so similar result, but the conclusion is stronger because you get the solution being extended to the whole half line, not just a compact interval, a whole half line. But on the other hand, f's autonomous. Okay, so how does that work? All right, so here's a conclusion. So let's just step through the proof a little bit quickly for this. All right, so similarly to the previous case, you have this general problem. Again, note f is autonomous. And you form a general rectangle. Or I guess it's not really a rectangle. It's more of an interval than a rectangle here. But I've just used R just to be a little bit more consistent. You have your general bound of f on M. And again, by Theorem 1, or a slight variant of Theorem 1, we know that the problem has at least one solution on this interval for this magic alpha. Here, not using a minimum because f is not dependent on t. All right? So you rerun the proof of Theorem 3, and you get a solution on this interval where big T sub m, or boldface T sub m, is this sum here. And then you take the limit. What happens as m goes to infinity? You get another divergent series by the integral test. Okay, again, that's it there. Okay, so we've just applied the integral test to a series. So the conclusion is that solutions to the autonomous initial value problem extend to the whole half line. Okay, so if you're looking for something to do, you can try to fill in the gaps of the proof for that particular case. Let's do an example. There's been a lot of theory. Let's just do an example. Okay. Here is, let's just take q equals a half, and this as my fractional differential equation. Okay, let me just see. So here's the problem, right? So I'm going to take q equals a half here, and this right-hand side, this is the autonomous case. So the right-hand side is just going to be this. And the claim is that for the initial value problem of order 1/2 with this f, there's at least one solution to this problem on the half line. Okay, so this will be Theorem 4, I think. I think this is theorem 4. There's just a typo. Okay, so what you can do here is choose a particular value. This actually isn't very good. Is choose a particular value for your phi of s. Say so, phi of s would be something like s plus 2, and that would be your phi of s to apply the autonomous theorem, or the theorem taking the autonomous case here. All right, so just forget about this corollary. That's a mistake. All right. Okay, sorry, there was a little typo there, so I apologize for that. Okay, so let me just share with you the references, a couple of references. These are not all the references. You can find more in the paper. So Diethelm and Ford, and of course you can find my video on the application of Weierstrass's polynomial approach to proving Theorem 1. Whew, okay, everyone, I'm exhausted. What did you think? Hopefully, even if you can't follow all the details in that presentation, you can get some idea or a bit of a taste or some flavor for the methods. Okay, but basically the little picture with the rectangles is the one that pretty much anyone can understand. If you have any comments, any questions, put them in the comment section, and I'll put a link to the paper when it's available. Thanks for watching, everybody. See you later. Bye.